Hello everyone, welcome to today's lesson on number systems. Right, so this is more of an introduction on, or perhaps a reintroductions on essentially what numbers are, right? How do we categorize them? How do you tell if something is a decimal or integer or that kind of stuff? Right, so this is pretty useful because at the end of the day, we want to understand that numbers is a language of pretty much all of science, right? Math is a very universal language that a lot of people around the world uses. So this is essentially some of the what's like a good I didn't really think about this ahead of time. What's like a good analogy? Not really like the past and present tenses, but we categorize numbers just so we have an idea of what we are working with, essentially. Okay? Well, that was a random yapping session. Okay, so number sets. A number set is pretty much a collection of numbers that share similar properties. Right, similar properties. So as you can see here, here are the main sets of numbers that we will encounter. First is the natural number. Right, that's probably the one that's easiest to remember. And we use those symbols here. Right, and yeah, it's an N with a little extra line there. Right, and a natural number is what we refer to as counting numbers. Right, and which means that it doesn't include decimals or zeros. Right, so what does that mean? Right, so it literally just means the numbers we use naturally. So if I were to count the students in my class, I'll start with one, right? 1, 2, 3, 4, 5, 6. If I were to count how many trees are there, I start with 1, 1, 2, 3, 4, 5, 6. Right, I never start with 0, unless I'm a computer. Right, oops. So natural numbers are essentially the numbers we use when we count something. Right, so that's why it's important to make sure that we do not include decimals and do not include zeros. I do not count 1.2 students to 1.3 students. I count whole numbers at a time. And speaking of whole numbers, right, we represent them with a W. No, so far so good. And with a dash, W is a dash. Right, so whole number just includes all natural numbers. But importantly, also includes zeros. Right, or, sorry, just zero. There's no ES there. Right, so it's pretty much just 0, and then 1, 2, 3, 4, and so on and so forth. Right, so think of whole numbers as just any number without a decimal. Right, that's all positive. So 0 and onwards, all the numbers without a decimal. Right, and as you can probably imagine, those are infinite numbers. Right, there are infinite amount of numbers for natural numbers, whole numbers, and so on. Next is integers. Of course, naturally, we will use Z as our little symbol here, because that definitely makes sense. Okay. Also because we use I for something else later. So integers, this includes all the negatives. Right, so it's essentially all the numbers with no decimals, but positive and negative. This is probably the most common one you will see. We will use the word integers a lot. So starting on 0, we got 1 and 2, -1, -2, to infinity on both ends. Okay, rational. Uh, of course, R will be too logical. We use Q here. And also because we will use R for something else. Rational numbers are all the fractions. So, a general rule of thumb, if you can put a number into a fraction, that's a rational number. Right? So that includes decimals, the and. That's very important. So decimals that have an ending. Or they repeat forever. So what does that mean? For example, we got -2/3 here. It's a fraction, so it's rational. We still got 0.75. Right? It's a decimal, but it ends. It's just 0.75, done. Right? And we also have things like 2.4 with a bar, or repeated. So 2.4 was a repeating line, just means that this 4 repeats forever. And that is also considered rational. Right? If you get something like, I don't know, 2.423 with a bar in front of it, or on top of it, the 2, 3 repeats on forever. Right, but that's okay. That is still considered rational. But what's irrational? That's when we use the I here now. Irrational numbers are decimals that don't end, aka things that cannot be put into a fraction. So for example, say pi. Right? So pi is 3.141529, blah blah blah, so on and so forth. Right? This is a decimal that goes on forever. Right? Basically, in a calculator, if you see that your calculator is filled up to the brim with decimals, chances are it will go on forever. Right? I will always try my best to not give you a decimal that where it ends exactly after, let's say, 10 digits on a calculator, right? If the calculator is full, that means the decimal goes on forever. Okay, square root of 2, also a good example. Right, if you type in square root in a calculator, it's 1.414 and so on and so forth. Right. And then yeah, like I said, it does not repeat, so it's irrational. And lastly, we got real numbers. Real numbers pretty much includes all the rational and irrational. Nope. See, I still got confused. Rational is Q and irrational is I. Okay. So pretty much everything above are real numbers. Pretty much every single number I can think of is most likely a real number. Right, which means that like we can kind of see here that all natural numbers are whole numbers, right? Because whole numbers is just 0 and all natural numbers, right? And all whole numbers are integers, right? Because again, a whole number is just the number without a decimal, and integers are all numbers without a decimal, whether it's positive or negative. So all whole numbers are integers. But remember, not all integers are whole numbers. Like -4, that's an integer, but it's not a whole number because it's negative. Right, and we can probably not probably we can literally visualize this in this little chart here, right? So if say let's take a natural number of I don't know 3, right? That's a natural number, and as you can imagine, 3 is also a whole number, and so 3 is also an integer, right? Because let's say we have 0 here, right? 0, as you can see, is not a natural number, but it's also an integer. And let's take -17 here, right? That's an integer, but it's not a whole number, nor is it a natural number. But -17 is a rational number, same as 0 and 3. Okay, so they're all kind of included within each other. And if you're curious, okay, or as a reminder, whenever we have a number by itself, we can see it as -17 or the number over 1, or divided by 1. So that's why technically it's still a fraction. We just don't write the over 1 because we're lazy. Okay, and if you're curious, the opposite of a real number is not a fake number, it's called an imaginary number. But we actually don't talk about it in this grade level. Okay, next, categorize the numbers. Okay, start with 8. So, it's a natural number, right? Because it's a because it is a whatchamacallit. It's a number we use to count with. Or again, it's a number without decimals. That's positive. Of course, it's a whole number. Again, number with no decimals, that's positive. No decimals, that's positive. Rational? Yes, it is. Irrational? No, it's not irrational. Okay? -100. Natural number? Nope. It's a negative number, so it's not natural. Neither is a whole number because it's negative. Integer, yes. It's negative with no decimal. Which means it's also rational, right? Because -100 is just -100 over 1. That's a fraction. Not irrational. 2 over 3. Not natural, right? It's not a whole number. Not integer. Right, rational, yes. Right, it's a fraction, so yes. That can be pointed to a fraction. Not irrational. If you're curious, 2 divided by 3, 2 over 3, is 0.6 repeating. It's a 0.6 repeated forever. Hence why it's rational. 0, natural, nope, nothing natural about that. Whole number, yes, that's by definition, it's just a number with no decimals, and 0. Oh, whoops, dropped my pen. Integer, rational, yes, yes, irrational, no. Pi, that's a fun one. Not rational, it's not a whole number. No integer, because it's got decimal. Right? Is it rational? Unfortunately, it is not rational. And because 3.1415 blah, 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 that goes on forever. So it's irrational. Negative 2.7. Nothing natural about that. Nothing whole about that. Almost an integer. It's negative, but it's not. It has a decimal, so it's not integer. Rational, yes, it's a decimal that ends. Oh, sorry, my head's covering it here. If it's rational, then it's not irrational. Okay, 4312 repeating. It's got decimal, so we know it's not the first three, right? Non-natural, whole, or integer. Rational, yes, it's rational, right? It's a number with a repeated decimal. If it's rational, it's not irrational. Okay, so sorting out the numbers. Okay, we can also write this as set notation. It's essentially a different way for us to indicate what is inside the set. Right? So why did the formatting get weird here? Oh, I hope on the actual worksheets it's not like this, but with set notation, right, we use those squiggly brackets to denote that this is a set. Okay, and then for natural numbers, we can start writing them. So we got 1, 2, 3, 4, so on and so forth. And of course, the numbers go on for infinity, so we don't actually have to write all of them out. We can just write 3 dots. Right? 3 dots implies that it just goes on forever, following the same pattern. So, right, we start at 1, and then we just go up by 1 each time. And of course, we just need those squiggly brackets on either side to denote that this is a set. Whole numbers. Okay, so 0. Generally, you just need like 4 or 5 numbers to denote that that's the pattern. Integers. Right, so as I showed earlier. Oops, wrong way. Right, 0, 1, 2. 3 dots on both sides to denote that they go on for infinity on both ends of the spectrum. Okay, here's a fun one, rational numbers. For rational numbers, now here's how we denote it. Right, we mentioned earlier that it's anything that can be put into a fraction. So, we could just treat it as p over q. Right, a number over a number. And more importantly, it's where p and q, right, so both the p and q are integers. Right, because if p is an integer and q is an integer, we pretty much just mixing and matching all of our fractions. Now, an integer could be -5 and 3, so our fraction is -5 over 3. Right, so that's how we denote it. Right, and in set notation, it looks like this. This is saying a fraction is pretty much a number over a number, where both of those numbers are an integer. Right, not a decimal, right? We cannot have 2.4 over -17.8 is not a fraction. And another caveat is that our denominator, cannot be 0, because that's illegal. We cannot divide anything by 0. Okay? So now let's do some practice with the sets. Right, so let's see. All whole numbers less than 4. Okay, we know the whole number we start at 0, right? And then we just go up by 1. But we can just stop there because it's all the whole numbers less than 4. So it's only 4 of them, right? 0, 1, 2, 3. All integers are multiples of 3. Right? It's all integers are multiples of 3, so there's no like upper or lower bound. So we know that on either end it goes to infinity. Multiples of 3. We can start at 0 here. It's probably the easiest. Right? Multiples of 3 will be things like 3, 6, so on and so forth, right? On the other side, -3, -6, so on and so forth. Right? So all integers are multiples of 3 is just like that. How about all odd natural numbers? So starting with our first natural number, which is 1, that's odd. We got 3, also odd. Right? Just like that. And that's it. Right? So again, we use the 3 dots as infinity to denote that, or 3 dots to denote that the number's going forever, but we still need 4 or 5 numbers in the front to kind of denote that here's the pattern we're going with that goes to infinity. But with that being said, that's pretty much it for today's lesson. Right, so like I said, this is important to know because this is how we sort numbers, and we'll be working a lot with integers. And like I mentioned, throughout this grade, I will always be referring back to, oh, let's put an integer here. It's like, okay, what integer goes here? What rational number goes there? Okay, so with that being said, good luck practicing.